Hi, I'm Carolyn Collins Peterson. Welcome to the Astronomers Universe, where we take a closer look at what professional astronomers are observing and what they're learning. In another episode of the Astronomers Universe, we explored the visions of star birth that astronomers are studying. These clouds of gas and dust that contribute their material to new stars are also the places where planets are born. And that's a very hot topic in astronomy research these days. The story of planetary formation picks up where star formation leaves off. Once a star begins shining, it's left with a flattened mass of material rotating around it, a circumstellar disk. The materials in that disk clump together, creating the seeds of planets, often referred to as protoplanets. Let a few million years go by, and depending on the mass of material available, a planetary system is born. Astronomers are finding more of these so-called protoplanetary disks all the time. The Orion Nebula has dozens of them. Each one may be hiding the birth of a planetary system. We know that there are other planets out there. Astronomers have found 353 planets in 278 planetary systems so far, and they'll be finding more as they apply a variety of techniques to search out new worlds. The seeds of planets begin as the tiniest particles in circumstellar disks. Those disks contain atoms of hydrogen and other gases, and dust particles made of silicates, carbon, and other organic materials. Those seeds come from stars that have died and scattered their elements out to space. In some cases, the dying stars were sun-like and ended their lives as planetary nebulae before shrinking down to become white dwarfs. In other cases, the stars were supergiants and blew themselves up in supernova explosions. Those catastrophic events scattered materials across space too, materials that eventually found their way to the circumstellar disks around newborn stars. Inside the starbirth disks, in the regions closest to the young stars, the gases were consumed or driven to the outer regions of the disk by radiation from the central star. In our own solar system, only the rocky materials could exist in the region closest to the newborn sun. This is because they're not as easily destroyed by the sun's heat and radiation. The rocky materials combined, forming ever larger planetesimals, colliding with each other, sticking together until Mercury, Venus, Earth, and Mars were formed, the terrestrial rocky planets. The regions far from the star, out beyond what astronomers call the snow line, are colder. In the early solar system, this is where the gas and ice were the predominant building blocks of the gas giant planets. Ice particles collided and stuck together, and those agglomerations mixed to make the proto-gas giants or accreted to form icy moons. In the most distant reaches of the early solar system, the leftover chunks of ice were pushed to the very outer limits, populating the two regions we now call the Kuiper Belt and the Oort cloud. The Oort cloud contains the oldest bits of primordial ice, mixed with dust and organic compounds that date back to well before the formation of the sun. It's a deep freeze full of clues to the stars that gave up the material that eventually became our sun, the planets, and us. Today, astronomers are modeling conditions of the early solar system, applying what they learned to other solar systems forming in our own Milky Way. Researchers are simulating chemical reactions between elements that are known to exist in a planetary birth cloud. Using sophisticated data processing and visualization software, they're modeling accretion theories and coming very close to understanding exactly what happened in the protosolar nebula long before life arose on Earth. What they learn will help us clarify our understanding of the new worlds still forming, hidden in clouds of gas and dust in our galaxy. For the Astronomers Universe, I'm Carolyn Collins Peterson, astrocast.tv.